Today I've got maybe like the best type of math problem, and that's a math problem that's very easy to state, but has an unexpectedly difficult or convoluted solution. And so in particular today, we're going to find the average distance between points in a unit square. So what do I really mean by that? Well, let's say we've got a unit square, so that's a square with side length 1. And we randomly choose the location of 2 points. I'll call them P and Q. And then we measure the distance between them. So this average distance is really the same thing as like the expected value. And we can do that with an integral if we figure out what the integral should be. Well, let's maybe get started in this. So let's give coordinates to P and Q. So let's say P has coordinate x1, y1. And then let's say Q has coordinate, maybe you guessed it, x2, y2. So that means we can use the distance formula, which is built out of the Pythagorean theorem, to find the distance between P and Q. And that's going to be equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Great. But now this expected value, or this average distance, will be the integral of this distance formula over all possible locations of P and Q divided by the four-dimensional volume of the unit cube. Luckily, that's really just equal to 1 because it's 1 times 1 times 1 times 1. Okay, so anyway, let's maybe write that down. So we've got this average is equal to the integral over, I'll write it as 0, 1 to the 4th power of the distance between P and Q, and then I'll just say dv4. So that's like our four-dimensional volume component, where, of course, this dpq is given by this down here. Okay, so now let's write that out a little bit more extensively. So that'll be the integral from 0 to 1, 0 to 1, 0 to 1, and you guessed it, 0 to 1, of the square root of x2 minus x1 squared plus y2 minus y1 squared. And then this differential volume component, since we're working with rectangular coordinates, can be done with dx1, dx2, dy1, dy2. So I think you can already see why this very easy to state problem is actually quite gnarly. Okay, good. So now from here, we'd like to do a change of variables that will start the road of simplification. And that change of variables that I make will be like this. So we'll set x equal to x1 minus x2. We'll set y equal to y1 minus y2. We'll set z equal to x2. And we'll set w equal to y2. Okay, so that is looking nice. So now, using some rules about change of variables, we know that this should be equal to, well, this guy with the variable changed. So that means this x2 minus x1 will become x. This y2 minus y1, well, that's going to become, let's see, y. Notice you might say those should be negative x and negative y, but it doesn't really matter here because we have these squares in here. So that's what's going to happen there. And then we'll also have to set up something or include something known as the Jacobian, which is the determinant of the matrix given by the partial with respect, or the partial of x1, x2, y1, y2 with respect to x, y, z, and w. Now, I won't work this out, but this just gives us 1. And it's not exactly the determinant of this Jacobian matrix. It's the absolute value of the determinant of the Jacobian matrix. This comes from the change of variables for multivariable integrals. Okay, so now let's maybe write our next step. So this is going to be the integral over, maybe I'll call this region D, where this region D is our new like 4-dimensional region, which is based off of our change of variables. So I'll just say that's a subset of R4. And now we have the square root of x squared plus y squared, and then another dv4, so we'll have to figure out what that is later. Okay, nice. So now note that x1 and x2 are both kind of gobbled up by x and z, whereas y1 and y2 are both gobbled up by y and w. So that means if we can get a handle on how the x1, x2 unit square transforms here, then we know how the integral or the region of the y1, y2 unit square also transforms. Okay, so let's make a picture of what's going on here. So let's say this is my x1, x2 region. So initially, I'm integrating over this region from 0, 1. So like I said, it's a unit square. And I'm going to color code each of these edges. So I'm integrating over all of this region right here. And this stuff in the middle. So now our goal, well, our immediate goal is to figure out what this looks like in the XZ plane. And we can do that by seeing what closed curve we get from the boundary here. Okay, so let's maybe see how this goes. So if x1 is going from 0 to 1 and x2 is always equal to 0, so that would be this yellow component, then that means that x is going from 0 to 1 and z is staying at 0. So this yellow turns into this yellow right here. So it's kind of the same line segment. Okay, nice. Now let's see what's happening over here. So over here, x1 is fixed at the number 1, whereas x2 is going from 0 to 1. So notice when x2 is equal to 0, we're at this vertex. And then when x2 is equal to 1, we're up here. Great. So let's maybe make sure that's a line. Good. And so this ends up being the line z equals 1 minus x, which isn't too hard to check. Okay, so that's looking good. Now let's figure out what's going on with the other parts. So this region up here, or this red line segment, I should say, that's when x2 is fixed at 1, whereas x1 ranges between 0 and 1. So that's going to give us something like this. Back here to this point, let's see, -1, 1. And then finally, to finish it all off, this region right, or this line segment right here, where x1 is equal to 0 and x2 is trending between 0 and 1, will finish this thing off. So we've got this parallelogram over here. So this is the region that we're integrating over. So now keeping this picture in mind, we can rewrite this integral, this like 4 integral, as an iterated integral where we've got 2 integrals on the outside and 2 integrals on the inside. So it's going to be the integral from 0 to 1, the integral from 0 to 1, and then the integral from 0 to 1 and the integral from 0 to 1 minus x of the square root of x squared plus y1 minus y2 squared. And then here we have dz dx dy1 dy2. Okay, so that doesn't capture everything over there. That captures what's going on right here. So this triangle right here. Okay, so that means we need to add on this other triangle. So that's going to end up being plus the integral from 0 to 1, 0 to 1, 0 to 1. And then now we're going from, let's see, our lower component or our lower curve is -x up to the number 1. So that would be this upper red curve of the same function here. So I'm running out of room, so I'll just put kind of parentheses for that same function. And then we'll have again dz dx dy1 dy2. Okay, so that's where we are after all of this calculation. So let's summarize that at the top and then we'll keep going. So this is where we left ourselves. So our average, which is kind of our goal, was equal to the sum of these 2 quadruple integrals. But notice the inner function does not depend on z, which is our innermost integral. That means the innermost integral is fairly simple. So let's take care of each of these inner integrals first and see what that leaves us with. So this first one is going to collapse to the integral from 0 to 1, 0 to 1, and then another 0 to 1 of 1 minus x times the square root of x squared plus y1 minus y2 squared, and then we have dx dy1 dy2. Again, that's from this z integral. And then next, we'll have plus the integral from 0 to 1, 0 to 1, 0 to 1. Oh, and I realized I have a typo right here. That should have been minus 1 to 0 because those are the x bounds of integration. The editor will fix that on the last board, so don't worry about it. Okay, then, so like I said, this is going to be minus 1 to 0, and then we'll have 1 plus x, and then the same function, x squared plus y1 minus y2 squared, and then we have dx dy1 dy2. Now we'll do a kind of more trivial change of variables here, and that change of variables will be to replace x with minus x. So that's going to turn this into a minus x, and then this is going to go from 1 to 0, and then this dx is going to turn into minus dx, which will change the bounds of integration here, allowing us to combine this integral with the one above, giving us 2 times this triple integral. 0, 1, 0, 1, 0, 1, 1 minus x, and then we have the square root of x squared plus y1 minus y2 squared, dx dy1 dy2. Like that. And now, indeed, we can do the same kind of thing with y1 and y2 variables that we just did with the x1 and x2 variables. And we're going to pick up another 2 copies, as well as a 1 minus y out front as we collapse this y1 minus y2 just to y. So again, this is essentially exactly the same thing we did already. So that's going to change this into a 4. It's going to collapse this triple integral into a double integral. It'll collapse this y1 minus y2 just to y, and it'll also insert a 1 minus y here and collapse this dy1, dy2 just to dy. So we're left with a kind of more friendly double integral. So now let's get to work on that double integral. So this is where we left ourselves on the last board. Our average value we're looking for was 4 times this double integral of 1 minus x times 1 minus y times the square root of x squared plus y squared. Now this x squared plus y squared gives us motivation to use something like polar coordinates. However, the fact that we're integrating over a square kind of pushes us against polar coordinates. So I think you can do this kind of appropriately with or without polar coordinates. We're going to do it maybe without polar coordinates, but with a trig change of variables, which is kind of the same thing. I think that probably all of these paths are about the same type of difficulty. Okay, so we're going to focus on the inner integral first, which is with respect to y. And we've got this x squared plus y squared, which motivates a tangent substitution. So let's set y equal to x times tangent of theta. That means that dy is x times secant squared theta d theta. And then that means that x squared plus y squared is x squared times secant squared theta. So that's by like trig identities. Furthermore, if y is equal to 0, that implies that theta is equal to 0. So that's because tangent of 0 is 0. And then if y is equal to 1, that means that theta is equal to the arctan of 1 over x. We'll just call that number alpha. Then we need one more thing. So if alpha is equal to the arctan of 1 over x, that means that the tangent of alpha is equal to 1 over x, which means the secant of alpha using trig identities is equal to the square root of 1 plus x squared over x. So we're going to need that as well. Okay, so there's all our like kind of long work in order to set up this trig substitution. Okay, so let's see what that leaves us with. So we're going to have 4, and then the integral from 0 to 1, the integral from 0 to alpha of 1 minus x times tangent theta. And then here we've got x times secant theta after taking the square root, and then an x times secant squared theta from the dy, leaving us with x squared times secant cubed theta, and then we have d theta dx. So we have something that looks like that. Okay, so now let's rewrite this a little bit. That's going to give us 4, the integral from 0 to 1 of x squared minus x cubed. That's this part that depends on x. And then inside of this x integral, we have the integral from 0 to alpha of secant cubed theta, and then minus x times secant cubed theta tangent theta. And then this is all d theta, and then outside of all of that is a dx term. Now, this secant cubed theta is kind of a classic integral. So I've calculated it on the channel many times before. I won't calculate it again. We'll just jump to what it is. And then the secant cubed theta tangent theta is actually quite a bit easier because this is secant squared theta times secant theta tangent theta. But secant theta tangent theta is the same thing as the differential of secant theta. So we have a nice change of variables that allows us to calculate that. Okay, so anyway, that's going to leave us with 4, and then the integral from 0 to 1 of x squared minus x cubed. This secant theta turns into secant cubed theta, secant theta tangent theta, and then plus 1/2 the natural log of secant theta tangent theta, like that. And then we finally have a minus x over 3 times the secant cubed theta from this one right here. Then we need to evaluate that all from 0 to alpha, and then we've got a dx here. Okay, so if we plug alpha into all of these trig functions, we get these values as described over here. So there's our secant, there's our tangent. And then if we plug 0 in, well, tangent of 0 is 0, so this cancels. That should be natural log of secant plus tangent, so that gives us natural log of 1, which is 0. And then secant of 0 is 1. So that's how that simplifies. Okay, so let's jump to that on the next board with just an x integral and all of those substitutions made as described by these. So after all of that substitution, we get the following single integral, which only depends on x. Now, portions of this single integral are fairly straightforward to calculate. Like, for example, if we take this polynomial into this radical expression or this radical expression or into this polynomial, those vary in difficulty, but I think you would calculate all of those with trigonometric substitution. So like, for instance, if we multiply x squared into this x squared in the denominator, we have an integral that looks like this to calculate. The integral from 0 to 1 of the square root of x squared plus 1 dx. We can make another tangent substitution here. So x is tangent theta, and that actually turns this into the integral from 0 to pi over 4 of secant cubed theta d theta. And I won't work out the details on that. But if we look at this guy right here, this one is actually quite complicated. And notice there are two terms connected to this. There's the x cubed and the x squared term. So for instance, one thing to calculate would be the integral from 0 to 1 of x squared times the natural log of 1 plus the square root of x squared plus 1 over x dx. And what approach would we use from this? I think you would probably use an integration by parts approach. And that's because we know how to take the derivative of this natural log object, but not the antiderivative. Whereas we know how to take the antiderivative of x squared. So we would set u equal to that natural log thing, and then dv equal to the rest. That being said, I'm going to end kind of the long integral calculations here because each of these would be almost like an interesting integral video on their own. And I'm just going to jump to the solution. So if you make all of this calculation, you end up with 2 plus the square root of 2 over 15. And then plus the natural log of 1 plus the square root of 2 over 3. So that ends up being the average value of distance between any two randomly chosen points in the unit square. And that's a good place to stop.